Hello everyone. In this video, we're going to give an introduction to eigenvalues and eigenvectors. We're going to do it through kind of a real-world example to start. So, what is this, at least semi-real world problem? So we're going to look at Crawfordsville and Indianapolis and their respective populations. So Crawfordsville is around 16,000. We'll use that number. And Indianapolis is around 890,000, like in the city and not the metro area, which would definitely be more. And where we're going to make up a little bit of the numbers is how many people leave one city for the other. Okay, so we're going to have like matriculation between the two cities. So I just simply don't have data for this, and these are definitely overestimates, but I'm mostly interested in like the relative terms and just numbers that don't completely suck. So let's suppose that 10% leave Crawfordsville each year for Indianapolis, moving for job opportunities, be closer to the, nightlife in the city, whatever reason. And let's say that like 1% from Indy leave for Crawfordsville. Okay, so again, both of these are definitely overestimates, and of course we're not considering the fact that people also move to other places and stuff, but just for this simple problem, it's a good introduction as to why we might care. So I want to ask the following question. So what population distribution among these two cities would create a steady state? And I say if any because, maybe these populations never reach like an equilibrium point and they just always are changing. But a steady state would be if, we hit certain populations in each city such that once 10% leave Crawfordsville and 1% come in to Indy, from Indy, that both populations of the cities stay the same. And then that would happen year after year after year once you hit that steady state. So how does one solve such a problem? Well, we can actually start involving linear algebra. So we're going to start with a population vector, just basically taking into account Crawfordsville and Indy. So it's going to be an R2, and it would just start as 16,000 and 890,000. And we'll just call this V naught for, like the initial vector, initial state, okay? So then the question is, how do I get from year to year? How do I incorporate this 10% leaving Crawfordsville and 1% leaving Indianapolis? So I can go back to, that sounds like a transformation to me, right? Like I'm doing some sort of mapping that changes the population year to year. So I want to find the matrix for that transformation. So I'm going to look at like the basis vector. So what happens if everyone is in Crawfordsville? Like 1, 0, this is like everyone's in Crawfordsville in terms of percents, right? So you could view like 1 is 100%, 0.1 is 10%, and so on. So if everyone is in Crawfordsville, then where does this go? Where does this basis vector 1, 0 go? Well, we know that 10% leave, so 90% remain, so 0.9, and then 0.1 are in Indy now, right? So this is Crawfordsville, this is Indy, Crawfordsville, Indy. On the other hand, if you have 0, 1, if everyone is in Indianapolis to start, only 0.1 or 0.01 will leave, right? Because 1% will leave, and so we'll get 0.01 in Crawfordsville and have 0.99 remaining in Indianapolis. Well, we know how matrices work for linear transformations. If we know where the basis vectors are, we know the matrix, right? We can assume our standard basis here, and so we just turn these into columns. So we get a 2 by 2 matrix, and we'll just call this guy A, right? And so if you wanted to know the population after 1 year, we could have the vector, we'll just call it V1. This is just going to be A V naught. If we multiply by A, that's the same as doing the transformation. That's the same as like doing the moving between cities. And so this would change the populations to what they would be after 1 year. And you can generalize this, of course. So after n years, you could have the vector Vn, and this would be A to the n V naught. Or if you want to view it just kind of step by step, right, it would be A times Vn minus 1. So you're just like multiplying that matrix by the vector for the previous year, right? So this is useful, but we're still not really there. what would it mean to have a steady state? Well, that would mean that 2 years in a row you have the same amount, right? So that basically means that for some k, right, so at steady state, this means that for some k we would have a to the k plus 1 v naught equals a to the k v naught, or vk plus 1 equals vk. And I'm going to rewrite this left-hand side to show what's kind of really going on here. It's a times ak v naught equals ak v naught. Let's just call this guy x. This is really saying we need some vector x such that ax equals x. This would be a steady state vector, okay? And so this actually leads us to the definition of eigenvalue and eigenvector. So let's pause to define those, and then we're going to see how it applies to this problem. So first, A is always assumed to be square in this case. So it's an n by n matrix here. And then we say scalar lambda is an eigenvalue for the matrix A if there exists some non-zero, and this is very important that it's non-zero, x in Rn with ax equals lambda x. So what's going on here? Basically, an eigenvalue shows up if there is this eigenvector. So this x in this case, this non-zero x, is called an eigenvector. That's really the one we want to focus on here. It's basically there's some vector such that A plays really nicely with it. That if you do the transformation, all you're doing is scaling, right? Because that's what this is saying. Ax turns into lambda x. So you just have x mapping to some lambda x. And that's a really simple transformation, right? You're literally just doing some multiplication by a scalar. And so this ends up being very, very nice when you're studying things. So eigenvectors are really nice things to make up a basis to describe maps, for instance. Because if you know all of your basis vectors, just go to some multiple of themselves, what's your matrix going to look like for the transformation? It's going to be diagonal. And that's super easy to deal with. So we'll get to that later, in class. But for now, let's turn this back to what does a steady state mean? And also, why do I care about this not zero part? Again, this would be really, really stupid if x is 0, because in that case, this just works for literally any lambda and any a, and doesn't say anything because it just says 0 equals 0. So it's only interesting if x is a non-zero vector. So that's why we have this constraint. Otherwise, there's just nothing really going on. So in the context of our problem, that steady state, we said basically we want ax equals x. So this means we want to see there is a steady state if there is an eigenvalue of 1 for a. So we want to see if lambda equals 1 is an eigenvalue of a. Right, because this is just ax equals 1 times x, if you want to think of it that way. So how does one figure out if this actually occurs? So let's think about this. So we're going to go back to the more general case. So we've got ax equals lambda x, right? Now I'm going to bring this over. So this is just the 0 vector. And I can actually factor out that x, and so I get a minus lambda I x is 0. Now you may ask me, why is this I and not lambda? Well, it needs to be a matrix over here. If I have a is 5 by 5 and then I just subtract by the number lambda, that makes no sense at all. What I really am doing when I multiply lambda, if I just have lambda, 0, 0, so that's lambda I, that's what that looks like, right? And I multiply by x1, x2, what happens? I get lambda x1, lambda x2. And so this actually does the lambda I x is going to equal lambda x. Okay, so that's why I'm doing that. And so if x is non-zero, this is exactly our definition for being, or a definition that we have of this matrix being singular, right? Because it has something besides the 0 vector that goes to 0. So we would say that a minus lambda I is singular. And now that we have talked about determinants, we know something else about this. We know that the determinant of this matrix must be 0. And this is actually how we find lambda, okay? So let's go back to our matrix. A was 0.9, 0.1, 0.01, 0.99. So if I want the determinant of A minus lambda I, that means I'm looking at this determinant here, 0.9 minus lambda, 0.1, 0.01, 0.99 minus lambda. And you can just kind of believe me on the math a little bit. So you would do it out a little bit. You get lambda squared minus 1.89 lambda plus 0.89. And if you factor this, it actually factors quite nicely. It's lambda minus 0.1 and lambda minus 0.89. And so we said that this determinant should be equal to 0. So set it equal to 0. We have found the two eigenvalues, lambda equals 1 and lambda equals 0.89. And so, hey, lambda equals 1 appears. And so there should be some eigenvector for that, aka we should have a steady state vector, okay? So how do we actually find that? Well, we actually just do a solution, right? So like if lambda equals 1, this means that ax equals x, okay? Or a minus I x equals 0. And we know how to solve things like this. This is just matrix times a vector equals 0. You can just do an augmented matrix. So if you plug in lambda equals 1 up here, where I just circled in red, this just becomes, right, 0.9 minus 1 is negative 0.1, 0.01, 0.1, and then 0.99 minus 1 is negative 0.01. And then we would augment with 0, 0. And if you go to the reduced echelon form, which is just like 2 steps, so pretty simple because these are multiples of one another, then you're going to get 1, 0, negative 0.1, 0 is your 2 columns. And so we would say that x1 minus 1/10 x2 is 0. And so x1 is 1/10 of x2 or x2 over 10. So you can just pick anything that works there. So the eigenvectors, any scalar multiple of it will still be an eigenvector. So in this case, I'm just going to pick one that's kind of easy. So I want my first entry to be 1/10 of the second. So let's do 110. Okay, so basically any time that you see, so what's the steady state? If Indy has 10 times the population of Crawfordsville, Seville, this is a steady state, right? Because this says that if I do my matrix, then I will get x back. So, if they reached, I don't know, 100,000 and, well, that wouldn't happen. So, 50,000, 500,000, something like that, right? Then you would have a steady state and it would stay like that forever. So your exercise, just going to be 1 here, is I want you to find the eigenvector for that other eigenvalue. So we said that lambda equals 1 and lambda equals 0.9 are both eigenvalues. So I want you to find the eigenvector for lambda equals 0.89. So think about what we did up here, right? We just kind of made lambda equal to 1 and then solved that out. So I want you to make lambda equals 0.9 and solve out, right, this a minus lambda I x is 0, okay? And so find the eigenvector for that. All right, that's it. Thank you for watching.